On the 3rd of June 1998, Ice Train 1, numbered 151, led by a motorcar 401051, was traveling from Munich to Hamburg. 287 people and 6 crew members were on board the train. After stopping at Augsburg, Nuremberg, Würzburg, Fulda, Kassel, Göttingen, and Hanover, it was approaching the town of Eschede when there was a loud bang, and a large metal piece pierces through a chair and barely missing Mr. Didman. Didman told the conductor, but right before they came back, it happened. The train derails under a bridge, which caused the bridge to collapse. 2 workers were immediately killed. In total, 101 people died and 88 were injured. But what caused this?
The disintegrated resilient wheel was the cause of the accident, but several factors contributed to the severity of the damage, including proximity to the bridge and flipping point, and the wheel being on a car near the front of the train, causing many cars to derail. The Ice 1 trains were originally equipped with single cast wheelsets, known as monoblock wheels. Once in service, it soon became apparent that this design could, as a result of metal fatigue, citation needed, and uneven wear, result in resonance and vibration at cruising speed. Passengers noticed this particularly in the restaurant car, where there were reports of loud vibrations in the dinnerware and of glasses creeping across tables. Managers in the railway organization had experienced these severe vibrations on a previous trip and asked to have the problem solved. In response, engineers decided that to solve the problem, the suspension of ice cars could be improved with the use of a rubber damping ring between the rail contacting steel tire and the steel wheel body. A similar design, known as resilient wheels, had been employed successfully in trams around the world, at much lower speeds. This kind of wheel, dubbed a wheel tire design, consisted of a wheel body surrounded by a 20mm thick, 0.79 in, rubber damper and then a relatively thin metal tire. The new design was not tested at high speed in Germany before it was made operational, but was successful at resolving the issue of vibration at cruising speeds. Decade-long experience at high speed gathered by train manufacturers and railway companies in Italy, France and Japan was not considered. At the time, there were no facilities in Germany that could test the actual failure limit of the wheels, and so complete prototypes were never tested physically. The design and specification relied greatly on available materials data and theory. The very few laboratories and rail tests that were performed did not measure wheel behavior with extended wear conditions or speeds greater than normal cruising. Clarification needed. Nevertheless, over several years the wheels had been reliable and, until the accident, had not caused any major problems. In July 1997, nearly 1 year before the disaster, Astra, the company that operates Hanover's tram network, discovered fatigue cracks in dual block wheels on trams running at about 24 km per hour, 15 miles per hour. It began changing wheels before fatigue cracks could develop, much earlier than was legally required by the specification. Astra reported its findings in a warning to all other users of wheels built with similar designs, including Deutsche Bahn, in late 1997. According to Astra, Deutsche Bahn replied by stating that they had not noticed problems in their trains. 23938. The Fraunhofer Institute for Structural Durability and System Reliability to Fraunhofer LBF in Darmstadt was charged with the task of determining the cause of the accident. It was revealed later that the institute had told the DB management as early as 1992 about its concerns about possible wheel tire failure. It was soon apparent that dynamic repetitive forces had not been considered in the modeling done during the design phase, 4, and the resulting design lacked inadequate margin of safety. The following factors, overlooked during design, were noted. The tires were flattened into an ellipse as the wheel turned through each revolution approximately 500,000 times during a typical day in service on an ice train, with corresponding fatigue effects. In contrast to the monoblock wheel design, cracks could form on the inside as well as the outside of the tire. As the tire wore thinner, dynamic forces increased, causing crack growth. Flat spots and ridges or swells in the tire dramatically increased the dynamic forces on the assembly and greatly accelerated wear. About the time of the disaster, the technicians at Deutsche Bahn's maintenance facility in Munich used only standard flashlights for visual inspection of the tires, instead of metal fatigue detection equipment. 5. Previously, advanced testing machines had been used, however the equipment generated many false positive error messages, so it was considered unreliable and its use was discontinued. During the week prior to the Eschede disaster, 3 separate automated checks indicated that a wheel was defective. Investigators discovered, from a maintenance report generated by the train's onboard computer, that 2 months prior to the Eschede disaster, conductors and other train staff filed 8 separate complaints about the noises and vibrations generated from the bogie with the defective wheel. The company did not replace the wheel. Deutsche Bahn said that its inspections were proper at the time and that the engineers could not have predicted the wheel fracture. The design of the overbridge may have also contributed to the accident, because it had 2 thin piers holding up the bridge on either side, instead of the spans going from solid abutments to solid abutments. The bridge that collapsed in the Granville rail disaster of 1977 had a similar weakness. The bridge built after the disaster is a cantilevered design that does not have this vulnerability. Another contributing factor to the casualty rate was the use of welds that unzipped during the crash in the carriage bodies.
In the end, a memorial was set for the train disaster. It has been 26 years since the train disaster, and hopefully a disaster like this will never happen again.